Good afternoon. Today we are going to take what we know about solving quadratic equations and what we know about graphing quadratic equations, and we're going to use that knowledge to help us solve graphic inequalities. For the most part, they work very much quadratic equations. There are, however, some subtle differences and some extra steps that we have to go through. But by the end of this lesson, my hope is that you know how to solve a quadratic inequality, both by graphing or by doing it algebraically, and that you should be able to describe what the solution sets look like. Before we begin, we're going to just do a quick review of what the inequality symbols mean, and then we're going to talk about what they mean in the context of a quadratic equation, which has a graph that looks like a parabola. So the first thing I want to talk about is what happens when y is less than, and when y is less than anything, we have learned in the past that this means that we're going to shade below, and we're going to use a dashed line. And you'll forgive me because I did not make mine dashed. I hope that a copy of notes that you have has dashed lines here. So I'm just going to color them in so that they actually look dashed. Ooh, there we go. Okay, so those are dashed lines. And in a parabola, if I'm shading below, then what that looks like in a downward facing parabola, it means that I'm going to shade the area under my parabola. And in an upward facing parabola, I'm actually going to shade, again, underneath the parabola, but the underneath happens to be below it, which, because the parabola keeps going up forever, will always be below that line. This one, y is less than or equal to, works similarly. Here we're going to shade below. So graphically, it's going to look like the graphs above. But this one, we're going to use a solid line, which I'm so well prepared for. Again, we're going to graph below a down opening. Actually, we shade below regardless. And I'm going to shade below my open or my upward facing parabola. It's really upward opening, isn't it? All right, it's the exact opposite over here. If I have y is greater than some equation or some number, then I'm going to shade above. And I should use a dashed line, which of course my version is not dashed. So I'm going to go ahead and self-dash. Is that a thing? Can I self-dash myself? Dash myself? Babble. Okay, and this time I'm going to shade above. In an upward opening parabola, I'm going to shade above. And in my downward opening, I'm still going to shade above, but it basically means the whole graph except for the parts underneath the parabola. Same thing here. This one is also going to, when y is greater than or equal to, I'm going to still shade above, but I am going to use a solid line. The shading looks similar to this one. I shade above my parabola, or I shade above the parabola. So a little bit different from linear inequalities, but the idea is relatively the same. Certainly the inequality symbols mean the same thing. So what are our steps? The first thing we need to do is write our inequality in standard form. Isn't that so cute? Oh, I can't form. We'll turn this into an R. I left myself 2 blanks. Wasn't that cool? Okay, then we graph our inequality. The easiest way to graph an inequality, folks, if you can use transformations, that's great, but that's really hard to do if you're given a trinomial. So just make a table using your calculator is a great way to do that. Y equals, type in your quadratic, and then go second table or second graph, and it will spit out the table for you. And then we're going to shade our areas based on our inequality. All right, so let's look at some examples. The first thing I'm going to do is I am going to, I'm going to think for a moment. That's what I'm going to do. I made a table, and I went ahead and did this for expediency, just so you don't have to sit here and watch me write down all these numbers. I'm going to notice the first thing is that my table up above, everything is referred to as y is less than or y is greater than. But in this case, if I let this function equal f of x, or for graphing purposes, a y value, then it's kind of flipped. So I'm actually going to flip this little guy so that I can use the table up above. You could still absolutely work with it in this form. It's just going to be a little bit easier if I have, if I write it as y is less than or equal to, because I'm really just completely transposing or reflecting the entire thing, x squared minus 4x minus 5. All right, so now based on this and my table up above, I can see that I'm going to use a solid line and I'm going to shade below. So I'm just going to make a note of that. I'm going to shade below and I'm going to use a solid line based on that little inequality. So that's good information to have. If I wanted to, I could try factoring this, and absolutely it would be factorable. If you use your factorizations, then I would do x squared minus 5x plus 1x minus 5 is greater than, well, I guess we switched it, so this would be y is less than. And I can go on and say that this is x minus 5, x plus 1, and I did the grouping there. And so I can see from this that y, one solution will be when y is less than 5, or perhaps when y is less than a negative 1. Not sure in this context. These give me my roots. If these were equal signs, then this would absolutely give me my roots. So my roots are at negative 1 and at positive 5. We'll talk on the next page about how to do this algebraically. But for our purposes, let's just plot some points. So at 0, if my x value is 0, my y value is negative 5. I'm going to put that point. 1, negative 8. 2, negative 9. 3, negative 8. And as expected, it's a parabola, so it makes that bowl shape. It opens up because my a value is positive. I'm going to sketch this skinny little parabola here. Notice I'm using a solid line. Put my arrows on it so I know it goes on forever. All right, so that's my parabola. And then I've already said that I'm going to shade below. So when I shade below, I can again look at the table up above, but I just want to shade below the line I just drew. And so I'm going to fill that in like that. And that is a graph of the solutions that make this quadratic greater than 0. Looking at this one, we've done the same thing. The first thing I would do is I would write this using a y value. Y's greater than x squared plus 4x plus 1. And I went ahead again and made our table. I can tell by looking at this that I'm going to shade above. And I'm going to use a dashed line. If you're using pencil when you graph, you have the added benefit that you can just draw the parabola and then use your eraser to sort of make a dashed line. It's a fail-safe method to use pencil for graphing. A lot of times I'm forced in notes to use whiteout because I forget to make a dashed line, but you can see here what we're doing. I'm going to go ahead and plot these points, -4, +1. I notice also that this is going to be an upward opening graph because the a value is 1, which is greater than 0. 3, -2. It takes me a minute to graph these things, and it is symmetric. So I am able to, and if I just go over here, I bet there's a point there. I can use my symmetry to help me out a little. And I'm going to go ahead and remember, shockingly, to make a dashed parabola. And in this particular case, we are shading above. So the numbers or the ordered pairs that represent solutions to this inequality will all live inside that shaded area. And that's a real simple way to find the solution set graphically for a quadratic inequality. All right, On the previous page, I alluded to this for a moment and then caught myself because solving graphically is a little bit easier if the numbers are pretty. Solving algebraically takes a few more steps, but we're going to go through that now, and you'll find that it's completely doable. Here are the steps that we need to follow in order to solve a quadratic inequality algebraically. The first thing we need to do is we're going to write an equation to represent the inequality. So I'm going to underline equation because now we're swapping the inequality symbol for an equal sign, and we're still going to write it in standard form, which, just to remind you, is ax squared plus bx. I feel like this should be ingrained in your brain by now. And we are going to set it equal to 0. Then we are either going to use factoring, or if you feel more comfortable, you can use the quadratic formula. But either way, you need to find what the x-intercepts are for the equation that mimics the inequality. Okay, those points, those x-intercepts can be graphed on a number line, and those are called critical points. And you saw them on the previous graphs. They were the x-intercepts. And so these are what we call our critical values. And then we're going to take our critical values and we are going to test, we're going to do some tests to see if they satisfy the original equation. And it's important that we always substitute those critical points back into the original equation. We're going to shade the true regions, or the regions that mathematically make sense. And we're going to remember, because we're doing a number line here, I don't know what's wrong with my blue pen. We're going to use an open circle if we have less than or greater than, and we're going to use a solid circle for less than or equal to, or greater than or equal to. So that's just a reminder from Algebra 1. Then once we shaded the true regions, then we are going to write out the solution using an inequality, an interval notation, or you can use set builder notation if you prefer that. All right, so let's dive in and actually put these steps into practice. The first thing I notice is that I need to write it in standard form. So step 1 says to write, step 1 says to put it as an equation instead of an inequality. Oh, so I'm going to do that. Write it as equal 8 instead of less than 8. Then the second thing I'm going to do is I'm going to put it in standard form, x squared plus 2x. I subtract 8 from both sides. Then I now have an equation that's set equal to 0. I am going to, third step is to factor this. And when I factor, I'm looking for two factors of -8 that add up to 2. And so I'm going to rewrite this as x squared plus 4x minus 2x. 4 times 2, 4 times -2 give me a -8. And when I add them, I get a positive 2. Minus 8 equals 0. I can do my grouping here. This is step 3. And when I do my grouping, I end up with x plus 4, because x is the greatest common factor between these two sets of terms. And then my greatest common factor on the other end from here would be a -2. I remember to use color. I get x plus 4 inside the parentheses, which we have learned is what I want, because basically what I did was I undistributed, or I factored out the x plus 4. So throwing things around here. One of my factors is going to be x plus 4, because that's what I factored out. And then the other factor is the part that remains after I do my factorization. So those are my two factors. Once I have factors, I set each one equal to 0 with my baby equations, and I solve, and I end up with x equals -4, x equals 2. All right, so now I have my solutions. What do I do next? The next thing I do is I'm going to plot those solutions on a number line. I don't draw the world's straightest line, so I'm gonna borrow a little card there to give me a straight line. I am going to plot my two solutions on here. And again, guys, you are the gods and goddesses of your number line. You can put the solutions anywhere you want. All right, so I'm not going to step it all out. I am going to put 0 in here because I love 0. It is a great test point, and you'll see why in just a moment. The next thing I'm going to do is I'm going to test some points. Not going to test solutions. I'm going to test things that are around the solutions just to see which numbers make my original equation true. Right? So let's see, this was number 4, just so you can keep track. So for number 5, I'm going to test some points. The first one I'm going to test, and if all possible, I suggest you try using 0. So we'll do that in a minute. I'm going to start left to right. I'm going to test something that's not -4. So maybe -5, because it's over here on the left of my critical point. So if I substitute -5 in for x, then I get -5 squared plus 2 times -5. And I'm asking myself, is that less than 8? -5 squared is 25. 22 times, let's see, I'll write it out. I'd make fewer mistakes. 2 times -5 is -10. So this simplifies to 15. Is 15 less than 8? And the answer is no, it is not. So this is not a solution. -5 is not part of my solution set. All right, I would like to test 0. Love testing 0. 0 squared plus 2 times 0. Is that less than 8? 0 squared is 0. 2 times 0 is 0. Is 0 less than 8? And the answer is yes, it is. So this is a solution. And then if I want to be very thorough, I would also test a number that is to the right of my critical point. So I might test 2, 3. I'm going to test 3. 2 is my critical point. So if I test 3, 3 squared is 9, plus 2 times 3 is, what is 2 times 3? That's 6. So I'm asking myself, don't put that there. Is is this less than 8? I can talk. 15 less than 8? And the answer is no, it is not. It is not a solution. So number 6 says shade the true regions. And in this case, our true regions happen to be where 0 lives. So I'm going to shade the area where 0 lives. I know that -5 is not a solution, so I would not shade over here. I know that 3 is not a solution, so I would not shade over here. And I remember that because this is less than, I'm going to use open circles to represent the fact that 2 is not a solution, but everything getting really close to 2 is a solution. So folks, that is how we determine what the solution set is algebraically. And then let's see, we just shaded our true region. So that was number 6. So I want to shade between my critical points. And then number 7 was to write our solution set in the form of an inequality or using interval notation. And so I'm going to use interval notation initially because it is less than. I'm going to use parentheses. -4 is my lower bound. 2 is my upper bound. And again, parentheses. I could also represent this as -4 is less than my x values, which are less than 2. And if I wanted to put this in set builder notation, just for grins and giggles, I would say x such that -4 is less than x, which is less than 2. All right, folks, that's how we solve a quadratic inequality algebraically. I'm going to ask you to pause the video and try looking at example 4 on your own. And while you do that, I'm going to work it out, and then I will show you all of my steps, but I'm not going to make you watch me do it. So pause and try it yourself. All right, folks. I went ahead and solved this one algebraically. This is the number line that represents my solution set. I first created an equation to represent that inequality statement. I put it in standard form, and because this one did not factor, I went ahead and used the quadratic formula, and I gave decimal approximation or estimations of the actual answers. The reason I paused it and did all of this ahead of time, and I'm just walking you through it now, is because using the quadratic equation just takes a little while. Step 4 was to go ahead and plot my 2 critical points on a number line, which I did. And then I tested some points. And when I tested points, I found that x equals -2, when substituted in, made this a true statement. 0 did not make it a true statement. And a +2 did make this equation a true statement. So I discovered where my solutions lied, and I went ahead and shaded those areas. And then I wrote my solution set as an inequality, using inequality notation and also using interval notation. I'm a total spaz, so I forgot briefly for a moment that you can't touch negative infinity, so that should be a parenthesis. And I remember that the symbol for and is a block letter U. Wanted to just, for one moment, talk about the fact that we graph these, the solution set, so that we can find what the inequality is to write, or we can find the solution set to write algebraically. We used a number line to do that. Don't be confused. There is still a parabola here. In this case, because our leading coefficient is 2, which is greater than 1, our parabola is opens upward, and it probably looks something like this. And my solution set lies outside or below my parabola. So the parabola is still, we're still solving a quadratic, and so there is still a parabola. This is just a way to algebraically figure out what the solution set is without having to do that graphing component. But it's still there, so I wanted you to see that. That's it for graphing inequalities, folks. It's just a couple of extra steps. Next class, we're going to do completing the square, which is inordinately fun and makes this look like a cakewalk. Until then, have a swell day.